Hello, I'm William Lee, and today myself and Daniel will be using experimental data derived from different experiments, which include analyzing the motion of a ball in the air and the launch of a ball in three different situations. We will then be using this data to make things like free body diagrams, finding the net force, and even using that net force to find the applied force on the volleyball. And ultimately, this will help us explain how video analysis has improved sports performance. So now we will be looking at the motion of the ball as it is in the air. Firstly, we will be looking at the position time graph in the x-axis. Looking at this picture, we can see that there is a constant velocity because of the linear fit. The constant velocity, by looking at our m value, which represents the slope, is 2.252 meters per second. Since the velocity is constant, we know that there will also be no acceleration.
Here we have the position time graph for the y-axis. Clearly we can see that there is a parabolic fit, so we know that there is also a changing velocity, meaning we have acceleration.
So now we will be looking at the velocity time graph for the y-axis. Firstly, we can see that there is a constant acceleration. Looking at the slope or the m value, we can see that the y has a constant acceleration of negative 10.66 meters per second squared.
We will now be analyzing the motion of the ball as it's being launched. To start, we'll be looking at the launch of the ball going vertical. Here we can see the position versus time graph in the y-axis. We can see once again that the object, in this case the ball, is speeding up or accelerating, which we'll look at further on the velocity time graph. From the position time graph, we can see that the object is accelerating. This velocity time graph for the y-axis confirms this. We can also see that there's a constant acceleration of 27.2 meters per second squared in the upward direction from a time period of 0 to 0.17 seconds. Now we will be looking at the net force on the ball and the applied force on the ball as it's being launched. First, we must draw our free body diagram to show the external forces acting on the volleyball. We can see that there's an applied force upwards and a force of gravity downwards. First, we must find the net force, so we can use that to find the applied force. To find the net force, we will simply multiply the mass of the ball, which is 0.450, by the acceleration of the ball, which is 27.2 meters per second squared upwards, which we saw from the slope of the velocity time graph for the y-axis. So now that we know our force, which is 12.24 newtons upwards, we can write our other net force equation and identify that the upward is positive. The equation is net force equals applied force minus force of gravity. Now, to find the applied force, we will simply rearrange the formula from which we will arrive at the equation of applied force equals net force plus the force of gravity. Since we know the net force, which is 12.24 newtons, and the force of gravity, which is mass times acceleration due to gravity, we will arrive at 12.24 plus 4.415, and therefore the applied force on the volleyball is 16.655 newtons upwards.
So now we will be looking at the launch of the ball horizontally by looking at the position time graph in the x-axis. Right away, we notice that there's a parabolic fit, which means our object is speeding up and accelerating. This also means that our object is moving at a non-uniform velocity. So looking at the corresponding velocity time graph again in the horizontal, we can see that there's a linear fit for acceleration, which means that there's a constant acceleration of 6.195 meters per second squared to the right. So now we will look at the net force and applied force of the ball being pushed horizontally. First, again, we will draw a free body diagram to represent the forces acting on the object. Firstly, we must recognize that there is no force of friction, and so we will only have three forces acting on the object: the normal force, the force of gravity, and the applied force. Since we know that normal force and force of gravity are equal in magnitude and opposite in direction because of Newton's third law, we can say that normal force will equal 4.415 newtons upwards, and the force of gravity equals 4.415 newtons downwards. Now we are left to find the applied force. Since there is no friction, we know that by solving for the net force, we can also obtain the applied force. Again, to solve the net force, we are going to multiply the object's mass by the acceleration. Therefore, after multiplying 0.450 kilograms, which is the mass of the volleyball, times 6.195, which is the acceleration of the volleyball, we arrive at 2.788 newtons to the right as our applied force. And this will also equal our net force, since we know that the normal force and force of gravity cancel out in this situation, and that there is no force of friction. Lastly, we will be examining the free throw launch of the volleyball by first looking at the position time graph. Looking at this, we can see that the velocity is not constant and is changing once again because of the parabolic, or I guess curve fit. And so, by looking at this velocity time graph, we can see that the y-axis has an acceleration of 23.03 meters per second squared upwards, and the x-axis has an acceleration of 15.81 meters per second squared to the right. So now we will be looking at the net force and the applied force on the ball. First, we will start off by solving the net force on the x-axis. And to do this, we will simply multiply the mass, which is 0.45, by the acceleration, which is 15.81 meters per second squared to the right. Doing this, we get a net force of 7.11 newtons to the right, which also equals the applied force on the right. Now we will find the net force in the y before finding the applied force in the y, since they are two different values, because we know that we must take into account the force of gravity. So to find the net force in the y, we will multiply the mass, which is 0.45, by the acceleration, which is 23.03 meters per second squared upwards. And this gives us a value of 10.364 newtons upwards. So now that we have our net force upwards, we can solve for our applied force on the y-axis. To do this, we must first specify that upwards is positive, then take the equation of net force equals force applied minus force of gravity, and rearrange it to find applied force. After doing this, you should arrive with the equation of applied force in the y equals the net force in the y plus the force of gravity. After summing all your values, you should get a final value of 14.779 newtons upwards, which is our applied force in the y. Now that we are done that, we can find the overall net force and the overall applied force using some trigonometry. First, we will solve for our overall net force, and to find the overall net force, we will first use the Pythagorean theorem. And so by square rooting 7.11 to the power of 2 plus 10.364 to the power of 2, we get a net force of 12.57 newtons. To find the angle of this overall net force, we can use SOHCAHTOA, and specifically TOA, which is opposite over adjacent. Because we're finding an angle, we will use the tan inverse and get an angle of 34.45 degrees. And therefore, we can say that our overall net force is 12.57 newtons north, 34.45 degrees east. Now we have to find the overall applied force. To do this, we will first find the overall applied force, again using the Pythagorean theorem. And after you square root 14.779 to the power of 2 plus 7.11 to the power of 2, we get an overall applied force of 16.4 newtons. Now, again, to find the angle of this applied force, we will once again use the inverse of tan to find the angle. By doing this, we get an angle of 25.7 degrees, and therefore we can say that our overall applied force is equal to 16.4 newtons north, 25.7 degrees east. So to answer the question of how video analysis has improved sports performance, an example would be with the free throw. By finding how much angle a certain applied force can give, you can give yourself the best chance of making a free throw successfully by possibly changing the arc of your shot or by changing your form. Also, athletes can look at their own movements after a game to see where they can improve. Recording and analyzing the player's performance after the game will let you catch small details and techniques that you may not have caught otherwise. Also, in baseball, a lot of hitters look at the velocity data and acceleration of the baseball to improve their timing at the plate. So that concludes myself and Daniel's presentation on how video analysis can improve sports performance using the data taken from several videos. We hope you enjoyed and found it informative. May the force be with you.